Alright, this is an introduction to aircraft structures. It's not something we're going to go into a lot of detail, but we do need to discuss this in light of the current design project. You have to know enough about what you're going to be designing into your aircraft, the design requirements of your aircraft, in order to properly select a structural design as well as material requirements for your aircraft. Now, structures is important enough of a topic that you'll have a single class in it dedicated to aircraft structural design in the fall as part of the Big Three. So again, we're going to just really cover some of the basics, just enough for you to be able to provide information on this in your semester design project. Now, you could really look at this from a standpoint of kind of comparing it to traditional structural design, design of buildings, for example, bridges and the like. And of course, we've been doing this not only for centuries, but obviously for millennia. In structural design of buildings is usually emphasized on very, very high safety factors and safety margins, such that a typical building will be able to carry much greater than its actual design load. Now, one of the things that makes aircraft design so difficult is the structural requirements for an aircraft to be successful, not only in terms of being profitable or being efficient, but just being structurally sound, are very, very small. So you don't have a lot of margin for error. If you end up making your aircraft too heavy, it's not going to fly. However, if you make the structural design too weak in order to try to lighten your aircraft, then your aircraft is going to fail. And this is really exhibited through a number of historic failures, and we'll give a couple of examples of these throughout the lecture. But really, one of the earliest of these is Samuel Langley's aerodrome. And as we mentioned earlier in the semester, Samuel Langley, who was the secretary of the Smithsonian at the time, is actually credited with the first successful unmanned heavier-than-air flight in 1901. And of course, this was part of his goal to be able to have a manned heavier-than-air aircraft development. And he tested this system, which he had scaled up from his unmanned flight, literally weeks before the Wright brothers flew. He actually had a pretty sound aerodynamic design. He had an excellent propulsion system, but he was deficient in his structural design, almost resulting in the death of the pilot. And really the issue was that he just wasn't sufficient in terms of scaling up the structural design requirements as he moved from the smaller prototype aircraft to the full-scale aircraft. Now, there are a number of examples that you can point to throughout the aviation industry that really give some kind of amazing conceptual realizations of how unique aircraft structures are. For example, the B-52 wing flexes a total of 32 feet from 10 feet down when it's resting on the ground to 22 feet up in flight. And so if you think about this 32 feet as a function of the overall 185-foot span, that's a substantial fraction that this structure is flexing. The Concorde, when it was in operation, actually stretched 7 inches during flight just due to aerodynamic heating. So grew over half a foot as it was flying. And the Space Shuttle Columbia, if you look at really both the accidents of the both Space Shuttle tragedies, it was really structural failures, that led to both of these. So the Space Shuttle Columbia specifically, failed during flight as it was re-entering the Earth's atmosphere due to an accident during the ascent phase when part of the insulating foam that covered the main external tank broke off and ruptured the carbon-carbon leading edge. And as it was re-entering the Earth's atmosphere, the heating, the ionized gas, the plasma in the atmosphere, due to the high speeds as it was re-entering at Mach 25, actually entered that internal structure and melted the interior of the supporting structure that held the wing on. Now, as we'll see from examples, all wings bend to some degree in flight, but most of them also twist as well. So as the wings are undergoing aerodynamic loads, we don't expect them to be static. So there is going to be some changes in deformation as you have the aerodynamic forces acting on the wing. We'll talk a little bit about aeroelasticity, but as we'll see, that's really even too complicated to cover in next semester structures course at the undergraduate level. Now, as we mentioned on the previous slide, safety factors for bridges and other buildings, can be very, very high. Sometimes really an order of magnitude greater than the design load. But for an aircraft, however, you'll typically see that your safety factors are on the order of about 1.2 to 1.5. The maximum design loads that you expect to see in flight. So you have a relatively small margin of say 25% to 50% where you might see some failure in some component of your aircraft due to structural limitations. Now here's an example of the Boeing 787 coming in on a landing. So as it's approaching its landing, again, we can assume that this is a quasi steady state attitude that it's in. So even though it's descending, that's a relatively slow flight. So again, it's more or less in level and steady flight. So we expect lift to be equal to weight in this scenario. But watch the wings as it goes through the touchdown phenomenon. And when we have weight on wheels, as the wings are unloaded, then you'll see them go to their static unloaded position. You can see the amount of flex that you had in those wings as it goes from the loaded to the unloaded portion of the flight. Now, there are really very important design considerations that we have to take into account as we're designing the structure of our aircraft. So first, the aircraft cost, and then things such as takeoff and landing distances, which are going to determine your runway considerations and the type of airport that you're going to be landing at, are all directly dependent upon the empty weight of the aircraft. So that's going to be not only mandated by things such as the FARs, but really driven by basic design considerations. As your aircraft gets larger and uses more material, that cost is going to go up. And what we'll typically see is that saving pounds on an aircraft can maybe save thousands, tens of thousands of dollars per pound on the overall cost of the aircraft. And we'll talk about this in another lecture specifically discussing weight prediction and considerations. So but you can also think about this from this standpoint of how much payload that aircraft is going to be able to carry. If you can save a pound of structural weight while still maintaining the same load carrying capability of the aircraft, that means that you can then carry a pound of payload instead, or perhaps a pound of fuel if you have the volume to carry that fuel as well. So obviously driving that weight down is going to be able to make your aircraft more effective and possibly more profitable as well. Now we also have to think about the philosophy around our design considerations for our aircraft, how we're designing this. And typically what we do not do is design around a fail-safe philosophy, meaning that those components will not fail during the life of operation or before those components are replaced. And that is usually due to the fact that requires a very high weight safety factor, and that ends up just becoming more costly than you can afford in an aircraft. So what we tend to do is take an alternative process, which is instead of fail-safe, we have a safe-fail procedure, where if a component fails, there's some alternative load path that is able to carry those loads. So that way no single failure will be hazardous to the aircraft that we're designing. Now obviously there are some things that if we have a certain component fail on an aircraft, we can't get around it. So we just want to make sure that those cases are very few and far between. So here's an example, kind of the worst case scenario, where we have a converted C-130 that's being designed for a really strenuous type of mission. And we'll talk about this in a few minutes when we look at the actual load that's being carried on these types of systems. But you'll see here as it's executing a high G maneuver, in this case going through a pull-up maneuver as it's preparing to deploy its fire retardant payload, that the wings fail and essentially break off, resulting in total loss of the aircraft and all of the crew on board. Now, as we mentioned previously, a lot of the forces that we see on the aircraft are primarily due to unsteady loads. So even though we'll be thinking about that on design consideration, that's really the lowest and the minimal types of loads that we're going to see acting on our aircraft. So almost always design from the structural standpoint of their aircraft around unsteady or dynamic forces acting on an aircraft, because those are going to be the most stringent loads that we're going to see for our aircraft acting during flight. So those loads are going to be acting on various places across our aircraft. So we can think about, wings as one example, but we'll also have to design the empennage, the fuselage, and things such as how the loads acting on individual elements, such as landing gear, are transferred throughout the rest of the aircraft. Because any load that's going to be acting at one part of the aircraft is really going to affect the entire aircraft as well. So we have to think about the load paths and how those loads are actually being translated or transferred from one part of the aircraft to another part of the aircraft. Now, of course, this has a big impact on what our VN diagram is going to look like, because as we said before, this is really a structural flight envelope for our aircraft. That vertical axis that determines what our load factor capabilities are. We usually use this as a design requirement. So for example, we might have a maximum load factor of 2.5. That's mandated by the FARs on our particular aircraft design. And in that case, then we have to design the structure around those loads in mind. Now, there are many cases where our aircraft are going to see loads kind of outside of potential normal operating loads. And here's an example of an L-1011. This is another airdrop, in this case particularly over LA. And think about what this aircraft is doing. I don't know how much payload it's carrying in terms of the fire retardant, but it's not uncommon for these converted aircraft to carry around 10,000 gallons. So you're talking somewhere on the order of 50,000 to potentially 70,000 pounds worth of payload being deployed in a very, very short period of time. And so you'll notice that as this aircraft is actually maneuvering, watch how the aircraft starts to dive as it's deploying its payload. And really what it's doing here in this case is it's changing its attitude, because as it's deploying its payload, the dynamic load on the aircraft is changing. The aircraft is getting lighter. And again, ostensibly, the nominal condition here is that the lift is going to be approximately equal to the weight of the aircraft. And if you're deploying a massive amount of load, in this case a significant fraction of the overall maximum weight of the aircraft, you have to be changing the lift at the same time that you're actually deploying this load. So think about what the wings are undergoing as it performs this payload drop and simultaneous maneuver. So as part of that, the structural design, testing, and verification of the structural design is really the most critical part of the overall aircraft design and verification process. So even though we don't talk a lot about the structural design in this class, it really serves as the foundation. If you don't get your structure to work, nothing else is going to work on your aircraft. There's no way that you're going to be able to make your aircraft successful if it is not successful from the structural design standpoint. So here's an example of the 787. Again, this is kind of hard to see in this particular picture. This is our structural test rig for the wings, which you'll notice is the fuselage right here in the center. And look at the wings. And so here, pointing out the starboard wing on the left side of the picture and our port wing on the right side of the picture here, you can see for this particular design test where it's tested to 150% of the design limit load. So in this case, our design limit as mandated by the FARs is 2.5. So they're testing 150% of that design limit load to make sure it's not going to fail. So that's the point where you want to make sure your aircraft is not going to fail. If it gets to 151% and fails in, that's fine. You're perfect. But you got to make sure that it doesn't fail at 149%. So you can see the extreme flex that these wings are actually undergoing. And trust me, if you looked out the window and saw the wings undergoing this type of deformation, you'd never notice because you'd be screaming along with the rest of the passengers based upon whatever the aircraft was doing to put the wings in that extreme loading scenario. So I'm not going to show this entire video here, but you can get an idea of the 787 wing brake test as it's going through this process. Again, so the jig that is built around this to push the wings through this simulated loading scenario, so that way you can measure the load and evaluate the point at what it exactly breaks at that 150% or greater mark. And you'll see this snap here in just a second as it reaches over that 150% design point and essentially breaks. And keep in mind that this is a partial composite wing design. So it doesn't just necessarily snap off. There's a failure in it. There's a lot of energy now that's stored up in these wings, and you can see how it essentially breaks in two. And it's, they're all happy because it failed, but it failed where they expected it to fail, which is exactly what you want from a testing standpoint. Is you've already gone through the process of designing this and you know where that's going to fail at, and so you're validating your predictions. So as an example, when we're designing an aircraft, we'll typically see, as we mentioned before, multiple load paths. So one way to think about this is you might have an internal structure of your aircraft that's carrying part of the load, and you'll have that designed in a certain fashion with certain materials. And then you'll have a skin, which is also going to carry some of the load, but it's going to be fashioned in a different manner, and it may be made out of or manufactured out of other materials. So they're each going to have separate properties. So imagine this from the standpoint where, let's say we want to carry a load of 1,000 pounds, but now we're using two different materials that each have similar load carrying capabilities, but they have very different material properties. So one is a chain which has very little stretch or strain capability associated with it, where another is a bungee which has a very large strain capability associated with it. So how would you then deploy both of these in order to be able to carry that load? So you would design this in such a way that if you want to carry that 1,000-pound load limit, you would essentially be able to design this around one system reaching or straining or stretching up to a point where it would carry your design load, which is going to be less than that overall load limit of 600 pounds for that individual component. And then once you have that in place, then you can couple that with the other material that you have that has a much lower strain capability associated with it. And now both of these materials would then be working in tandem. And this kind of basic philosophy is how we approach a lot of our design requirements for aircraft when we start putting these different pieces for our aircraft together. Now, as part of this, again, we can think about this from a philosophical standpoint and how we're going to carry that load for our aircraft design. There are really two basic structural design philosophies or structural design configurations. One of those is you can think of as a truss design, where you have your load carried by an internal frame and a truss, but none of that load is carried by the skin. And you can think of this as very traditional in our wood with fabric doped early aircraft designs, where you have a frame and truss system, and the aerodynamic loads are really just immediately transferred from the skin directly to that truss, and they don't carry any of the loads themselves. A more modern approach is the monocoque approach, where you have some of that load being carried by the internal frame, but you also have a stressed skin. So that stressed skin serves dual functions. It's not only transmitting your aerodynamic loads directly to your internal frame, but it's also carrying some of that load as well. And in this case, if you follow this particular path, then it usually leads you to a lower weight as well. So it's a weight-saving philosophy using this monocoque process. And for those of you who will be in Speedfest next year, this is essentially the approach we use with composite wing aircraft, where we have that composite skin carrying part of the load in addition to the internal frame that's carrying portions of that load as well. Now, there are many different structural elements that we'll have across an aircraft, all kind of with unique configurations, and we're not going to go through all of them, but you have primarily three common structural elements. The skin, as we mentioned, stiffener elements, which provide a stiffening capability to different components of the skin, and then those internal truss components, primarily made up of different beams. And you'll notice that we have kind of very specific elements that we'll refer to. In wings, for example, we'll primarily have spars, which run along the span of our wing, and then ribs, which run along the chord length of our wing. So the ribs will be carrying loads that's transferred from the skin directly to the ribs, and then that load is transferred from the ribs to the spar, and then the spar transfers that load directly through the wing box structure to our aircraft fuselage. And the fuselage itself will usually have frames which run along the stations from the nose to the tail of their aircraft. And then we'll have longerons, which run down the axis of the aircraft. Sometimes we might have a keel, which is typically going to be located on the lower side of our aircraft. That will carry main loads for the fuselage, but also loads from the wing and the gear. Now, all of our materials in our aircraft may experience both tension and compression. Think about what the load is happening on the wing as it goes from positive g-forces or positive load factors to negative load factors. So at some points you'll have compression on the upper side, tension on the lower side, and as you reverse those load factors, the tension and compression will swap from the top to the bottom. So we'll analyze or utilize a lot of structural design and analytical approaches in 4253 in the fall to be able to go through a process of analyzing the loads and then designing around that. Now, as examples of wing designs, you can have multiple ribs and multiple spars, and that's going to be typical configurations for most modern aircraft wings, where you'll use many different ribs along with multiple spars. Typically, at least one spar located at the quarter chord and a smaller spar located at the 3/4 chord. But you can use many different spars across the wingspan as well. And there'll be lots of different ways that you can combine these together to provide weight savings for your aircraft while still being able to carry the same load. Primarily, depending upon how you utilize the ability to minimize your weight while maximizing your cross-sectional moment of inertia. So you really want that capability to transfer those loads from the cross-section along the length to the fuselage portion of your aircraft. Likewise with the skin, you can have lots of different ways that you can design the load-bearing capabilities of your skin. Now, for most aircraft, modern aircraft, these are typically going to be pressurized. Not always, lower altitude aircraft like general aviation aircraft will usually not be pressurized, but anything that's typically going to be over 15,000 feet in terms of its flight capabilities, including modern airliners and other transport aircraft, are going to be pressurized. So in this case, you can think about that fuselage as a pressure vessel, and then you can use the same pressure vessel equations that you're already familiar with to go through the process of designing the load carrying requirements and looking at the hoop and axial stresses acting on that pressure vessel. And once you know that, then you can understand the process that which you'd go through to reduce the weight of that pressure vessel to carry that same load by using things such as longerons or stringers or hoops to be able to carry some of that additional load. Now, as you recall, our traditional stress-strain behavior for materials, as we're deforming that material, increasing that strain, will have a linear region where our stress is increasing linearly with that strain or deformation until we get to some yield point where we'll then experience a nonlinear plastic deformation regime until we get to the point where that structure fails. Now, this behavior is highly dependent upon the individual material characteristics, the behavior in particular of where that yield point is at, the plastic range, and then ultimately that failure. That failure point can be much closer to that yield point than is shown in this particular conceptual figure, for example, or it could even be farther away. Now, to analyze this individually, we have to go back and look at the individual elements and the behavior of each one of those elements. In particular, looking at our tension and compression forces on those individual components, as well as bending and shear forces. Again, this is going to be in more detail than we need to go into, but since you're already familiar with these components and these different behaviors, as well as the material properties that you've taken in other classes, it's now just a matter of taking these pieces and putting them together in the construct of our aircraft design. Now, obviously, we're going to also have to consider how these loads are being transferred through joints as we're connecting different pieces together, and think about how those loads then are being transferred from one component to another component. And it's usually when we see failures, it's pretty common to see the failures within these particular joints, because these are going to be the regions of your highest stresses. Whenever you're putting a hole in a material, you're obviously going to have stress concentrations located near these holes in your material, as well as a greater propensity to have critical material deficiencies or defects within these particular areas. So you might have a crack, and that crack would then propagate under that stress concentration, and then that might result in a failure. Now, what we often see in aircraft failures is the impact of fatigue. And so rather than a failure being immediate, what we're going to see is that material start to degrade over time as it goes through cyclic loading. Think about this in the context of your wing as it becomes loaded and then unloaded, loaded and then unloaded. For every flight that it goes through this process of being loaded to extremely high loads and then unloaded back again repeatedly, perhaps multiple times per day. So you might have this process happen 1,000 times or more a year. So you obviously end up with a lot of cyclic fatigue possibilities. The best common day example that I can give is a paper clip. Take a paper clip and you think about, well, I want to snip this paper clip in two. You go to get a set of shears. Think about the energy that goes into that to be able to snap that thin paper clip in half. But if you want to do that easier without going through the process of using a mechanical implement, then just do some cyclic loading. Typically in about 10 cycles, you'll be able to take that paper clip and fail it. So this is very similar to what you'll see with aircraft as you go through the process of cyclic loading over and over, repeatedly. You're going to eventually have any component is going to reach its limit and fail. So you have to think about the material properties and how those cycles are affecting the behavior of that. Classic example from the aircraft industry is the de Havilland Comet, which was a British aircraft design. And really ostensibly, the British at this time were far ahead in the commercial jet transport aircraft design. So they beat everyone else to the punch with this particular aircraft. But they lost 2 aircraft in flight due to fatigue loading, primarily because no one had a good understanding of the high fatigue failure design or the failure behavior for this particular alloy of aluminum, or as the British call it, aluminium. So they didn't understand this until they went through the process of analyzing the data from these 2 aircraft failures. And you can see here that they did occur at those stress concentrations near the window. Now these failures still happen today. So again, it's not uncommon for aircraft to suffer structural failures in flight. You want to design your aircraft. We saw the example of the B-52 from the controls lecture, which lost its vertical stabilizer. Even though that's obviously a critical failure, the aircraft was still able to safely land. Here's an example of a 737 that was flying across the Pacific Ocean from the continental U.S. To Hawaii, when it also suffered a serious failure in the structural skin of the aircraft, where you have a whole section of that upper structural skin essentially torn away. The aircraft was still able to safely operate and land, even though there was loss of life of one crew member, which was essentially that individual sucked out of the aircraft at altitude. Now, as I mentioned earlier, we're going to do a pressure vessel analysis for the structural design of our pressurized aircraft members. And so from this, assuming that we have a cylindrical aircraft design, which is going to be for a structure that has a high aspect ratio. That's going to be the most optimum and lowest weight solution for us. We can analyze in both the hoops and the axial stresses using our pressure vessel equations. From this, we can then add elements, such as longeron, stringers, and keels, to be able to reduce that overall structural capacity or add to the safety of factor with our structural design. Now, as a rule of thumb for this, the skin thickness is going to typically be 1/2000th of that of the overall radius of your pressure vessel, which is going to end up in most aircraft skins being on the order of a millimeter or so. Fairly small if you think about it from the standpoint of a structural design. That of itself is something that it'd be relatively easy to bend without the presence of those other stiffening elements that you have around the structure. Then we can use our basic equations for both the hoop stress and the axial stress to determine what those limits are based upon those panels. Now here's an example of the Boeing 787 skin. You'll notice that this is a composite design. So there's a composite skin along with composite stiffeners, which are added in to provide additional stiffness, not necessarily strength, but provide less bending for that structural design. So let's look at an example of a Boeing 737. What we're going to do is calculate that total delta P that's acting, assuming that the interior is pressurized to 13.5 psi, and we're going to be operating at a nominal altitude between around 35,000 feet, which gives us something around 3.5 psia. So that means our delta between the interior and the exterior is going to be around 10 psi. Now the 13.5 is actually pretty high. So we're kind of, erring on a very conservative side in this case. Most airliners will typically operate around 11 or 12 psi, and even modern aircraft such as the 787 is going to still be on that kind of that lower, higher end, around 12 to 13 psi. We will not be operating at 14.7 psi for most of our aircraft. So our 737 skin is 2024 T3 aluminum. It is 0.063 inches or about 1.6 millimeters thick. And our overall diameter that we have is 137 inches. Note that pretty closely follows that rule of thumb that we talked about earlier, where the thickness is about 1/2000th of the overall diameter, or sorry, 1/1000th of the overall radius that we have for the aircraft. So from this we can calculate both our hoop stress and our axial stress on the order of 875 psi for our hoop stress and just over 5,000 psi for our axial stress. We can then go back and compare these to the yield stresses for the 2024 T3 aluminum, which I'll leave as an exercise for you, but you'll obviously see that these are well below the yield stresses for that material. Now, one of the pieces that we're going to look at in detail is the design of that, the wing, or the calculation of the loads on the wing. Now, what we do is first we're going to treat the wing as a cantilever beam, one end of that fixed to the fuselage, the other end of that free to deform. And we're going to look at both the loads and the moments acting on that cantilever beam. And we're going to do this by simple superposition, meaning that we're going to look at individual loads such as the lift from the wing and the structural load of the wing, add those together, and then from that calculate the overall deformation of the wing. So from this we're going to look at the planform span loading on the wing. So consider how that lift is being generated on the wing and what loads it's being generated under. Obviously, we have to be able to sustain lift is equal to weight, but then we need a positive load factor as well as a negative load factor limit. So typically 2.5, for example, for that upper load factor, at least as a minimum. That's the lowest that we're going to typically design around. So once we know what that lift distribution is for that nominal cruise configuration, we can multiply that by 2.5 to look at our design limit. Now, the particular approach that we're going to use is something relatively simple, which is called Shrink's method. And what it uses is an average of the elliptical and trapezoidal loads acting on the wing. And so we're going to take the average of those two to be able to give us a nominal load acting on the wing. So this is just a simple approach to be able to go through an overall estimate of that lift distribution and the load factors acting on the wing. Now, for our structural loads, we can look at these as either distributed loads or point loads. For example, the fuel and the structural weight, since those are spread across large distances, we're going to consider them as distributed loads, while our point loads, such as the engines or other structural elements, are going to be considered as point loads acting on the wing. So we'll use this spreadsheet called loads to be able to calculate this, and from this be able to go through a process of estimating first what those aerodynamic loads are, and then from that calculate both aerodynamic loads and moment distributions, and then add those up with all of the structural loads acting on the aircraft, the structural weight of the wing, the weight of the fuel distributed over different portions of the wing, and then our point loads such as our engines, to give us our total load and moment distribution. Now, what you'll notice in many cases is our maximum may not be at the root of the wing. So due to the fact that our wing is going to be typically acting in the opposite direction as our overall lift of the wing, that weight is going to tend to reduce the overall load and moment requirement from our wing just based upon aerodynamic considerations. And if we're clever about how we place our engines on the wing, those will also reduce the structural load requirement on our wing. So there's a benefit in terms of placing things such as engines on your wing, because that will reduce the overall load that your aircraft sees within flight. Again, a little non-intuitive until you think about it, with the fact that the engines are creating a downward load while your lift is creating an upward load throughout flight. Now, it is possible then to brace the wings, and this is a traditional approach for many small aircraft as well as historically larger aircraft. And in this case, you can treat these also as point loads acting on different portions of the wing in order to be able to reduce the overall structural load requirement acting on the wing. Now, there have been a number of recent designs, particularly by aircraft companies such as Boeing, looking at novel new braced wing concepts in order to provide transport aircraft with a much larger aspect ratio and thus much more efficient lift to drag profile using braced wing concepts. So that may play somewhat of a comeback in the future, but that remains to be seen. Now, there are multiple ways that you can then transfer those wing loads to the fuselage. Traditional approaches include wing box carry-throughs as well as ring frames, where that load is distributed circumferentially around the fuselage. There are simple approaches where you essentially have a single bending beam that's connecting those two wings together, or you can have a strut braced approach where that wing is then free to pivot about the fuselage. Many times, to be honest, what you'll see in an aircraft is one really large bolt that essentially connects the wing to the fuselage, and all those forces are transferred through that single bolt element within the structure. Now, there are a couple of structural design philosophies to keep in mind as you go through the overall structural consideration and configuration for your aircraft. First is to keep the load path simple. You want your design relatively easy to analyze, and in that case, if it's easy to analyze, it's also going to then be relatively straightforward to manufacture and assemble. This helps keeps your costs low. Don't overcomplicate matters when they don't need to be. You have to make sure that you're analyzing all 6 components of the structural loads acting on your aircraft. So you have to consider not only the forces, which is what we've primarily focused on so far, but also the moments acting on your aircraft. How is the wing not only being bent along the span, but also being twisted by the aerodynamic moment acting on it, for example. Also, a statically determinate structure is going to be preferred over a statically indeterminate structure, and this will give you the minimum weight potential for that particular design. So thus, for a given set of loads, you really want to be able to determine that there's one set of reaction forces for that particular structure. You also want to design each structural component in mind to serve multiple functions. Don't think of any particular structural component in aircraft as a unitasker. You want to have a wing spar, for example, carry both span-wise bending as well as vertical shear loads, but also provide support for things such as landing gear on takeoff and landing, structural loads for fuel tanks that you have on your aircraft, as well as the ability to attach things such as point loads from the engines and payload stores to those various components as well. Also, the subsystem integration requirements must be considered early on in the design process, primarily as you're going through the process of not only manufacturing and installing different components, but during the overall life cycle of that aircraft, you want to be able to have your customer come in and be able to make not only repairs but also inspections of the various structural elements. That aircraft may be in service for 50 years, so you have to have the capability for the end user to be able to come in and look at those key elements. So both accessibility and operability of that should be considered paramount as part of that design process. Now, I'm not going to spend a lot of time, looking at some different examples. Mainly at this point, we really have to think about things such as consideration. When you're designing elements such as spars within your aircraft, where's that gear going to go if you're going to have a stowed gear? Think about where everything has to fit in relation to those structural elements. Do you have enough volume to put everything in there? Do you have room for your gear? Do you have room for your fuel tanks if you have a wet wing? Are you going to have room for your servo mechanisms for your ailerons and flaps within your wing? How are you attaching the engine to your wing if you have a pod mounted or a nacelle mounted beneath the wing? So you have to think about these different considerations as you're going through this design process. Also think about the load paths. Typically the easiest ones to consider are things such as landing. When you're landing, how are those gear loads transferred through the rest of the aircraft? As you're applying thrust throughout flight on your aircraft, how is that thrust being transferred from the engine to the rest of the aircraft? Through the engine mounts, to the wing or to the fuselage, or from the engine mounts to the fuselage directly. For specific wing designs, what we're going to typically be looking at is a wing that is going to have a hollow interior. Something that gives us a large cross-sectional moment of inertia is preferable. So all things being equal, a thick wing is going to tend to be lighter than a skinny wing, assuming that they're carrying the same load. You also have to think about how that load is being transferred from the wing, from something such as the wing spar to the rest of the wing, as well as the aerodynamic loads acting on the skin and how those loads are being transferred along the skin to those primary structural elements that then transfer those loads back to the fuselage. You can go from something that is relatively simple, for example, a single spar with a sandwich monocoque skin, or something that is more similar to a conventional truss design, where now you have a membrane skin where that load is being transferred directly to these truss elements and then back to your spar. And that's going to finally lead you to an overall structural design. Now, at this point, again, we don't want to think too much about the detailed elements of the design. We're not looking for how thick, each rib needs to be, or even really how many ribs. What we're looking at is a conceptual design. So we want to be able to have enough detail so that way the next phase we'd be able to give this to the structural design team, and then they could figure that out. How many ribs do you need? How thick do each one of those ribs need to be? How much load is this individual spar carrying? So we're really looking at this from an overall configuration standpoint, but also material selection. Where in this case, we're denoting two primary component materials. For example, the red being a steel, the white being an aluminum alloy, as overall conceptual materials for our aircraft to be designed out of. So when you start thinking about materials, you need to look at some various material selection considerations as part of your design process. Specific strength, specific stiffness, what environment is the aircraft going to be operated in, what's the fracture toughness, what's the manufacturability of the material that you're using, minimum gauge limitations, and finally availability and cost of the overall material. Traditionally, you're going to be looking at a range of metals that you can choose from different aluminum alloys, titanium, and steel, up to things such as carbon fiber materials, modern manufacturing options, or even some potential classical materials such as wood. So these materials kind of run the entire gamut from things commonly used every day to fairly exotic materials. Keeping in mind that it's not uncommon for an aircraft to really push that limit in terms of strength to weight ratio for various materials, particularly when we're looking at aircraft that might be designed for very extreme environments, maybe such as a space shuttle type of design or a fighter aircraft. We might be willing to pay more if we're really able to push the capabilities of those individual materials. So we're going to look at a range of different materials as part of our overall trade study. Now this includes composite materials. When we start looking at composite materials, that allows us to look at other options as well, rather than kind of traditional overall designs, particularly sandwich configurations where we can distribute loads are over a much larger volume. Now, one thing that we had to consider when we start looking at composite materials is these are sometimes going to be more difficult to predict. And so in this case, we may actually be looking at a lot of empirical models for our composite materials rather than looking directly at traditional analysis. Now, primarily, we're going to be looking at things such as density, yield stresses, and relating those back to a reference material. In this case, we're going to use the most common material that we'll typically see for modern aircraft design, which is 2024 aluminum. So that's going to be our baseline, both in terms of our tension, our buckling, and our bending loads for our aircraft. And you can see from different materials here that we have a wide range of different configurations, but they're all fairly closely benchmarked to those particular design elements. So as an example, we can compare a minimum thickness for fuselage skin using titanium, magnesium, and fiberglass, and comparing it back to that 2024 aluminum as a reference material. In this case, each looking at the stress and then the required thickness of that material to meet those same pressure vessel requirements, and compare both at overall stress as well as the resulting thickness. So we can see fiberglass has the best performance, but it has the lowest temperature limit, difficult to repair, and also difficult to work with. So that may, rule it out depending upon the types of environment that we're looking for. Titanium has the highest temperature limit and a performance comparable to that of the fiberglass, but it's also very, very expensive and difficult to machine. We can see the magnesium can also withstand high temperatures, but in this case has a much higher thickness than the aluminum does, and that's going to have a large impact then on our aircraft design. The final thing we're going to mention here is really just as a consideration, is thinking about how our aircraft structural design is going to behave, not only from a static load standpoint, but also from an aerodynamic or dynamic load standpoint as well. In this case, we're looking at the overall science of aeroelasticity, which is looking at combination of both the aerodynamic forces and the structural deformation, both static and dynamic, and looking at the interactions that are going to occur between these. So when we start to combine all these together, we're going to look at the aerodynamic forces, the elastic forces that we're going to see from structural deformation, and then the inertial forces given the weight of our structural design. We can see some really unique things from an aircraft design and operation standpoint that we may not see in other more traditional designs. So as an example, here is a B-47 flutter test in a wind tunnel. So we can see the wing body flutter that's occurring on the aircraft model. And so when you're thinking about the overall structural design, not only from the behavior of the aircraft and then flight operational environment of the aircraft, but you also have to think about the structural loading over long periods of the aircraft as well. And in many cases, these become very, very difficult to predict, and you often don't even see these encountered until the actual flight test. And so notice in this particular case, for our DG300 sailplane, they're being activated when you apply control surfaces under specific configurations. And even under conditions where you have extreme resources to go through the process of analysis, this is a very complex phenomena, and you can still have scenarios where you might have unexpected aeroelasticity behavior occur. And where this really becomes important then, if you start to look at the fatigue impact that this is going to have, rather than having your aircraft now have cycles on the order of ones or tens in a day, now you might have cycles that are happening on the order of hundreds, thousands, or even 10,000s during a single day. So this can reduce the overall lifetime of your aircraft. So these things must be taken into account as you go through this process, even though it's really far beyond our ability to analyze at this particular stage in our studies.